Today we have Dr. Faisal Shah Khan. I want to read out his biodata. Dr. Faisal Khan is a mathematician working as a principal investigator, Center of Cyber Physical Systems at Khalifa University, Abu Dhabi. Dr. Faisal Khan earned his PhD from Portland State University. Professor Khan was a former assistant professor, Department of Applied Mathematics and Science in Khalifa University, UAE. He also a technology advisor of Quantum Computing Incorporate, USA. His research interest includes including mathematical model for optimizing, developing the next generation quantum computing processing, interference, quantum devices, cyber physical system context, application of quantum computing of different industries like financial, traffic control system, as currently he is working on the COVID-19 problems. These are the brief biodata about the Dr. Faisal Khan and myself, Dr. Kunal Das. I'm from India, Kolkata. I'm an assistant professor of Acharya Prafula Chandra College. I'm working around 15 years and in this quantum computing domain. I did my PhD from Kalyani University in 2014 on the subject of quantum computing. And I was the first in West Bengal who achieved a degree from in a subject of quantum computing. This is my short biodata, and today my work is as a moderator. So without wasting time, I want to call Faisal to start your lecture. And if audience has a attendance, I can say that you can, if you have any question, you can write your questions in a question answer box or chat box. It is open for you. You can write a question answer. So after discussion of with the Faisal, we can float these questions for better understanding of these question answer sessions. And I also have my own questions that I will ask to Faisal. So Faisal, please, you can start.
Thank you very much. Awesome introduction. Thank you so much. Very kind of you. And of course, I should thank Dave and Helen and Amalok, who have all kind of, organized this, put together this meetup. So I'm very grateful for that. Let me see if I can share my screen. My slides. There you go. All right. So now the topic is Nash embedding, and it's actually a mathematical result, which is from quite some time ago, I guess 1952 or 54, something like that. And it is by the same John Nash that found quite a bit of fame in the subject of game theory. So one could say that this is actually one of his less well-known results, right? It's maybe even accurate to say it's a more well-known mathematical result, more impressive mathematical result, but less known publicly. So what I would like to talk about today, of course, is just how you can use this to help. Yes.
Dr. Faisal, could you please make your full screen presentation?
Sorry. Yes.
Yes, that's good.
So thank you, Kunal. So I would like to talk about how this can be used as a sort of a toolkit for all the tools needed to program a quantum computer by a classical programmer, right? Which is the main issue in quantum computing, that you have programmers who are classical beings like ourselves, and we want to send signals which are at some stage classical, but then they turn into quantum signals, right? And somewhere along the way, we have to be in a position to deal with the noise that comes up in the process. And my claim would be today that Nash embedding is the toolkit that will kind of let us at least ask the right questions, if not get the right answers to begin with towards that end. So I'll start with some context about computing. And I have a few pictures that I gathered for this purpose. There's the Babbage difference engine from 1822. That was more than 100 years ago, almost 200 years ago now. And it's actually a computing device. It would compute some polynomials, some values of polynomials, and of functions of sorts. But the big important thing here to note that I want to point out, in fact, is that it's a mechanical device, right? It's built of cranks, and it's got a whole bunch of shafts in it. And you would literally basically move one of the shafts like this, rotate it, and that would allow the computations to take place. So computing, of course, has come a long way since then. But if we were to think that that was, 200 years ago was actually something, it's really ancient, it's too old, and a long time ago that people came up with a mechanical computing device, that would not be actually very accurate. What in fact we can see in history, if you look carefully, is instances of other mechanical computers, computational devices like this one right here. This is from 2000 years ago. So, this is the anti-Kaithera mechanism. Of course, this is just a rendition of it, a modern rendition. The mechanism was found about 90 years ago in a shipwreck, I think off the coast of Greece somewhere. I don't remember the exact location, but it was pretty worn out, right? But this seems to be what it did. It would predict cosmological phenomena, and it was a mechanical computer. Now, of course, the computers that we're used to are not mechanical, right? These are actually electronic computers. And these came about in 1945, really, or maybe a few years before that, during the Second World War. The picture right here that I have is the ENIAC. It could be considered to be a first commercial electronic computer. And it would basically do basic calculations, no more different in many ways than what the Babbage difference engine did 100 years before that. But the big jump here was that this was an electronic device, right? We were using things which were not cranks anymore, right? Shafts and cranks, which is what the other two devices had to implement the calculations. So this was a big jump, is the point I'm trying to make here, to go from mechanical calculators or computers to electronic computers. And of course, now we have, I've put this picture of an Apple Mac just because it looks nice and sleek. This is kind of what we expect electronic computers to look like today. And they do look like that. They're very much more efficient than the ENIAC was, obviously. They're orders of magnitude much faster, much more efficient than the ENIAC from 1945. So the evolution, these devices have evolved quite a bit, and have reached a sort of a pinnacle, which is great. But we are running into some barriers, which I'll talk about a bit more in the next slide. But my point is that what seems to be happening is this next generation of computing that's coming up, right? The notion of a quantum computer. And I've put a slide here, a picture of a component in Honeywell's quantum processor. Looks nice and metallic, very shiny and sleek, which is great. But performance-wise, of course, it's very limited. The issue there, of course, the limitation comes from the fact that noise keeps getting in the way, right? So much the way noise was dealt with when the ENIAC was around, and it was dealt with successfully until we have an Apple Mac, something similar would have to happen when you look at Honeywell's current quantum computer or processor, and you try to imagine what they're going to look like, or what it's going to look like several years down the line, and it would be error-free. So that's kind of what the vision is. So the issue that's coming up, of course, is Moore's law, right? And Moore's law, of course, is the one which roughly says that you can keep shrinking. I mean, very roughly, it's basically saying that you can keep shrinking your size of your chips, right, on your personal computers or any computer, any kind of hardware device. You can keep increasing the number of processors, right? And the idea is that then the question comes up is that, would that ever stop, or can we keep on doing it? Now, there are people who say that Moore's law is dead, so I've got a little link for that down there. It's somebody at NVIDIA who said that last year, and that may well be the case. On the other hand, if you assume that it's going to keep on happening, keep on continuing the way it's supposed to continue, then yes, the natural outcome would be a quantum processor, right? And what you see today is the first generation, if you will, of those quantum processors. You could call them quasi-quantum, because they're not fully quantum in the sense that there's a lot of noise in the system. And of course, that's what we would like to mitigate. And so kind of to build up on that, here's some examples of several technology platforms for quantum processors. There's a few by IBM Q, Rigetti, and D-Wave. They actually use superconducting qubits. So they use superconducting technology to build qubits, and the qubits are connected to each other to share information, quantum information ideally, using solid hardware wires. On the other hand, we have another platform which is popular. It's used by IonQ and Honeywell, and these are atomic qubits in the form of trapped ions. And the information is shared between the qubits using lasers, right? So you don't actually have physical wires in a very crude sense, the way we kind of imagine them to be, right? Some kind of a physical wire that I can touch. And if I put my hand through a laser, I mean, it's a physical quantity, it's a physical object, but I won't be able to feel it necessarily. So it's you know, it's a little bit less physical in that sense. But these two platforms exist, and people are working on them. But of course, the point is it's noisy. All this hardware, despite the technology platform, is noisy and faulty, and the hardware you get is error prone. So we'll talk about this now, right? This issue of noise. So let's bring to the foreground what noise is. Before we talk about noise, we have to say what information is, right? And information is, you know, there's a whole theory of information. There's several theories of information. The most popular one is Shannon's theory, right? It's most practically useful, I guess one could say. And the point is that information is a probabilistic phenomena. So you sort of think of events happening and you say that each event will happen with respect to some probability. Now, the smaller the probability of an event, the more information that event conveys when it happens, right? So you know, people have known that I've got a bald head for some time now. But tomorrow, if I showed up and talked to Kunal via Zoom and had a full head of hair, that would be a lot of information going towards Kunal, right? That would be a very unexpected event. So that would be a notion of like a lot of information went to Kunal somehow, right? But of course, if I show up tomorrow in the same kind of, you know, get up, if you will, right? And it would be totally expected and not much information would get conveyed. So that's kind of how people try to capture the notion of information. Of course, you define things like entropy and so forth, but you don't have to get into that necessarily. But the point, the reason I wanted to bring information, the notion of information was so that I can talk about noise. And I guess noise would be any phenomena that affects the probability of an event, right? So if there's some true probability with which an event occurs, but if that probability gets affected by some physical phenomena, or well, physical is what we will think of, then that would be something you would consider as noise, because it's getting in the way of the true information that was supposed to get across, right? So that's what we will call noise, right? Now, noise in a quantum system would be any phenomena that affects the quantum source of probability of the event. Now, what we understand today is that there are classical probabilities or probabilities generated by classical phenomena, classical physical phenomena, and then there are probabilities generated by quantum physical phenomena. So that's what I meant when I said classical versus quantum source of probability. So that's kind of the fundamental model, right? And it's pretty fundamental. That's the standard model, you could say. Everybody imagines or views noise in that sense, to my knowledge at least, in a very broad sense. And that's what we'll take noise to be here as well. So what would that mean for me, for somebody who's looking to sort of, you know, deal with this noise? Well, I'll have to first say that any physical process that diminishes the quantumness, right? I'm trying to deal with noise in the quantum system. That's my quantum processor. So what would that be? what would that, how would I deal with it? How would I kind of capture that? So you would capture that by saying that any physical process that diminishes the quantumness, right? The quantum source of probabilities, if that quantumness of that source is being diminished somehow, then I have noise in the system, right? I can't tell if it's actually a classical system or a quantum physical system that's giving these probabilities. Heat is a ubiquitous, everywhere, ever-present source of noise, right, in quantum systems. If you have a classical computer and you try to interface that with one of these quantum processors I put up on the screen earlier, there would be a lot of noise sent from these devices to the quantum processor in the form of heat, of the flow of ensemble of electrons, billions and billions of them, right, carrying this information across to a device that's supposed to be working in a very pristine and noise-free environment where the quantumness is preserved. So that wouldn't be a good match, right? That's a bad interface, and that's what we want to figure out, how that happens, how to do it properly and in a productive way. Quantum measurement, it's a fundamental idea of how things go from the quantum to the classical realm. That itself is noisy in a certain way. So a lot of that, I would talk a lot about that later on, actually. But I want to model these things mathematically. So I'll say that any physical phenomena that diminishes quantumness, I would like to think of that as any sort of a transformation that's going to not preserve the topology, which is the study of shape of my state space, right? Everything happens, physics happens in some kind of a space. Classical physics happens in Euclidean space, and quantum physics happens in a different space. They have some kind of a shape. So if that shape gets contorted, then presumably there's noise in the system, right? So I'll say that is a source of noise, right? Topology. Differentiable structures are very important because that's how we measure rates of change, how things are changing over time. So if there's some sort of a distortion taking place in the differentiability structure, then there'll be some sort of noise in the system itself. And finally, and that's kind of the main focus of the discussion, geometry, right? How the geometry of your space getting twisted or contorted leads to noise in the system. So really quickly, just some basic examples. Here's what topology does, right? It basically says that a coffee cup and a donut are the same thing because they both have exactly one hole in them, right? So if you think about it, you can transform a donut into a cup and vice versa. So that's kind of what topology studies, the shape of space. Differentiability, this is the idea of taking tangent spaces, tangent planes, if you will, right? If you're in low enough dimensions, and try to see how you can linearize things. So that's what differentiability does. Geometry is just something we all study from for a lot longer than the other two topics. Looking at lengths and angles and how they stay congruent or the same, right? So this is kind of the idea here. So how does noise come about? It comes about because, well, especially in a quantum system, right? It comes about because of what I said earlier. Qubits behave according to the laws of quantum physics, but programmers like us, and this is of course pertaining to programming a quantum processor, we are classical entities. We live inside the classical realm, and we have to interact with these quantum processors. So the interface is noisy, right? If you're not careful. And that's the fundamental problem actually in quantum physics. How do you go from one realm to the other? And it's coming to the forefront with the advent of quantum technologies, right? It's becoming more crucial, if you will, to address. So to talk about all these things, I'll go through the mathematical setting of physics and quantum physics and classical computing and quantum computing. I did promise that I'll keep the mathematics to, well, a minimum, but you may feel that it's too much. I don't think it would be the case, but this is the least I could do. If I had taken any more further amount of mathematics away from the talk, it would have taken away from the usefulness of the talk. So let's talk about classical physics here. We have a mathematical model for this. It's the Euclidean space, right? This is the space we all live in, right? And we experience every day. We put real numbers to coordinatize it, right? And then we call it Rn. So R2 would be the Cartesian plane, right? That's where we draw our parabolas and circles and all those things and do our basic mathematics and calculus. Here's an example I'm trying to give. I have an arrow that's sitting in the Euclidean space E2. I'm going to put coordinates there, right? So I get the Cartesian plane with real numbers. And now I have the benefit of having two, there's a lot of vector space structure that comes along with this. In particular, I have 2 degrees of freedom, which I call basis elements in my vector space. And now I can express my arrow, which was capturing some physical concept, right? Arrows are very useful in physics. They carry magnitude and direction at the same time. So I can express that black arrow in terms of the degrees of freedom in red, right? And in particular, if I wanted to transform them, I could do it with some kind of a transformation like that, right? So I could stretch the arrow, I could rotate it, I could shrink it, that sort of thing. And that's you know, I'm not saying that's all of classical physics, but that's a lot of the classical physics that's out there. Right? Now, for classical computing, a similar kind of setup is useful, right? So you still take your Euclidean space as the space where things will happen. Your classical computings will the computations will take place. But instead of instead of coordinatizing with the real numbers, you're going to use lattices, right? So this is going to give rise to binary computing. You could use 0, 1, 2 lattice. Right? It'll give rise to ternary computing and so forth. So really quickly, you have 2 binary values, 0 and 1. I take another copy of them, right? And I get 4 binary outputs. And now I can do computations, right? I could do some kind of a transformation, some computation that'll take 0, 1 to 1, 1, 1, 1 to 0, and so forth. So that's kind of the idea of space, you know, where things happen and how they play a role here in mitigating errors eventually, as we'll see. So now, of course, when we come to quantum physics, things get complicated pretty quickly. So I'll get into this, of course, but maybe this is a good time to take a very quick break and see if the audience or anybody from the panel has any questions or comments. I see there's one. So the topological way of deriving quantum state is interesting, as it has no reduction. But Kunal, do you want to take the question?
Yes. The topological way deriving the quantum state is an interesting, as it has been in noise reductions. But how can we associate that state with the state of physical state?
Right. Yeah. So if I understand the question, it's asking about topological quantum computing and how do you realize that physically, right? I mean, what technology platform are we going to use?
Next one is I think moving towards. Okay.
Really quickly, yeah. So the Microsoft, of course, has had, in fact, for 20 years, a pretty big program that's been dealing with topological quantum computing. It's been known for a while that you need non-abelian anyons, right? They're a certain kind of a particle. And I haven't been following it lately, so there may have been developments that I am not familiar with. But the point is that you need those anyons to be realized somehow in a lab, right? And then you can do all these topological computations. So that's that, I guess, for that one.
Okay. The next one, that question is, I think moving towards the parallel quantum computing may reduce the noise. In nature, the time is redefined.
So the question I'm seeing is quantum computing limited to Euclidean or Cartesian space? What about Hilbert space, which is theoretically infinite? Is that the one, Kunal? Is that the question?
Yeah.
So I'll talk about exactly the Hilbert space in this slide and onwards. So I'll address that, I guess, then. So you can ask, I guess, later on if you feel you still have a question about it.
You can continue. Still.
Okay. So shall we
Oh,
continue?
Another question. Is quantum computing limited to Euclidean or Cartesian space? What is about the Hilbert space?
Yeah,
He's
that's the one.
talking about the Hilbert.
Yeah, that's the
Hilbert
one.
space.
So I was saying I'm going to actually address that just now, as soon as we get back into the slides. That's what I'll talk about, the Hilbert space.
Okay, now we can continue.
Shall I continue then?
Yes.
Awesome. Thank you. So the question, of course, came up, right? That what about Hilbert space? So let's talk about that. That's where the quantum stuff happens, right? So quantum physics is mathematically modeled by a projective space. We call it CPn-1, and it's coordinatized by complex Cartesian coordinates from our complex number plane that we're familiar with. The complex plane basically looks like this. It's just the Cartesian plane, but with a slightly different algebraic properties. So they're not the same thing algebraically, but C1, the complex plane, and the Cartesian plane are the same thing as sets. Right? But we want to look at the algebraic properties, so then they become different, right? And that actually difference makes a role in how quantum computing takes place. So for n equals 2, we have two complex planes, right, intersecting each other orthogonally. And of course, we need 4 dimensions to see how that happens. And we can't, but we can certainly visualize this in our mind, right, in our mind's eye. So this is where we start. And the question could be, why do we need complex numbers, right? Certainly is a very natural question. Why is it that when we start modeling quantum physical phenomena, we need to resort to complex numbers and not just simply real numbers? Now, there are, of course, ways you can sort of define mappings which take away the use of complex numbers, and you can do things completely, completely by using real numbers. But efficiency and some sorts of like the ability to talk about quantum mechanics becomes a bit less. Becomes a bit more difficult if you use only real versions, right, of your space. So that's why people like to keep complex numbers in the picture. So let's see what we have here in terms of why, right, in a bit more detail. So the reason why we use complex numbers comes from the 2-slit experiment, which is a fundamental experiment in quantum physics. What we have is a photon source, and we have a detector on the other side. We have a wall in the middle, and it has 2 holes in it, 2 slits, through which the photon can go through, right? And what happens is that if you think of a photon as a classical object, it would go through either one slit on the top, right, with probability P1 right here. It'll take this path maybe. Or it can go down through this slit, maybe taking this path, right? And that probability of that happening, that event happening, is P2. And then on the other side, you detect the photon one way or the other. So what you see here is the axiom of additivity from probability at play, right? So if I was to now say that what's the total probability that a photon went through this wall and got detected on the other side, you would say, well, the probability of each of these events, right? The photon going through the top slit or the bottom slit, these are mutually exclusive events. So the probabilities should just add up, right? And when they add up, you should have the total probability as P1 plus P2. And that's what you can actually verify in a lab with classical objects, right? But photons, of course, are not classical objects. And we know that because when you do this experiment with photons, you don't see this classical physics, this additivity axiom from classical physics. You see something very different, which involves complex numbers. You're forced to introduce a notion of probability amplitude, which basically is a complex number, which replaces the probability of going through the top path or the bottom path, right? The probability of being detected on the other side by the detector of the photon, right, is now the length of those 2 complex numbers added together and then squared, which becomes a real number. So it's still a probability, It's a real number between 0 and 1. But the way it becomes a real number is quite different, right? It's no longer just the two probabilities adding up. So what you then see is that you have a revised axiom of additivity, which says that it's not the probabilities of mutually exclusive events that add up, it's the probability amplitudes that add up, right? And this is why probability amplitudes are actually a fundamental feature of quantum physics, right? You say this is why quantum physics is different than classical physics. So how do you go from probability amplitude to probabilities? Well, here's some math, right? Nothing too fancy. I should say here's some algebra, right? Math is too broad a term. So if I do some algebra here, right, I'll leave it for those who are comfortable with it. I'll leave it up on the screen. But my bottom line here is to get to this point here. When I do all these calculations and substitutions up here, I see that the probability amplitude that I had on the screen, on the previous screen here, right, of the photon being detected on the other side, resolves to the probability where I have the original probability numbers P1 and P2, plus this term right here in red, which involves the cosine and the difference of two angles, right? So the point is that if your object is classical, then this red expression doesn't appear, and you have the usual axiom of probabilities adding up together. But if your object is a quantum object, then you actually have to deal with this extra term. So this is what you could call is a quantum probability, right? And the noise would appear here, right? When we were talking about how does noise affect the system? Well, if noise is going to reduce the quantumness of some quantum physical system, it'll affect this red part right here, and affect the eventual probabilistic behavior of the physical object. So the point is that the quantum is where the phase is, right? So this is what we call phase here. So I'll take a question at the end of this slide. So P equals P1 plus P2 plus this expression. Phase is the difference of these two angles here. And it's a geometric property that comes up from complex numbers. In the previous slide, I skipped through a bunch of substitutions. In those substitutions is where you see the angles come up first. And they basically are a way to represent complex numbers in the complex plane, right? And you can always do it using polar coordinates. So this is where this is coming from. The point here is that there's a notion of decoherence, right? Or dephasing that takes place here, that can take place here. And this is when the angle difference here, right, is a multiple of pi over 2. When that happens, the cosine term goes away to 0, and you're reduced to just a classical, right, the original probabilities that you imagined a classical object would follow, right? So the idea is that decoherence is a form of noise, right? And we'll see that measurement actually produces decoherence later on. Okay, so I guess I can take questions, Kunal. Do you want to? I have 2 questions here appearing. 3 questions.
Yeah, 2 questions are there. One is the P1 and P2 is a complex number, because the question is given, are the 1 and 2 subscripts referring to each component of complex numbers? This is
no,
the one question.
Yeah, so this question I can answer quickly. The 1 and 2 subscripts are just saying there's a probability P1 and probability P2. I went through the slides really quickly. So those are real numbers. P1 is one of them, representing the probability that the photon went through one hole in the wall. And P2 is another real number, representing the probability that the photon went through the other hole in the wall.
And the second question is a rate component. This rate component or rate term is it a correlation or the cosine similarity estimates? Is it correct?
Yeah, so I am not familiar with the term cosine similarity estimate, but it is the law of cosines. That's exactly
or
right.
Is it, or is saying that, or is it distance metric?
It's a distance. So if you think of it as a generalization, which it is, right? If you think of it as a generalization of the Pythagorean theorem, then yes, you're measuring distance, right, between 2 points, where the distance is, the angle is no longer 90 degrees, right? So it is definitely the cosine, law of cosines, and it's playing a role. That's a question, right? Why do we see the law of cosines in here? And that has to do with the fact that the geometries are connected, right? And so when we talk more about the complex projective space, we'll perhaps see how that happens.
Any other questions? I think so many questions in the chat book also.
Yeah, those are the ones I'm looking at.
I'm reading out. Where exactly does the noise affect the variables? In the rate equation means where is the rate component? Okay, where is most likely the wood effect, or does it depends on type of or amount of noise? Is it depend on the amount of noise?
Right. Thank you. So I can answer that one by saying that measurement actually affects this red quantity, right? When you try to decide whether your photon went through the top or the bottom slit, you're basically making what's called a measurement, right? Quantum measurement. And that basically collapses the quantum feature, right? Which is this phase difference or angle difference. You lose information about it, right? So that actually affects, so that plays the role of noise, right? So there is, the question is, where exactly does noise affect the variables in that red equation expression, right? Well, exactly there, where the red part is, right? That's where the noise plays a role when you make a measurement. And there's another question, Kunal, I can read it here, I can see the chat.
What is the physical meaning of thetas?
The thetas are, so I went quickly through it, but thetas are basically, so remember we had two complex numbers, A1 and A2, right? Those measure how far your, so if I express those numbers as in polar form, right? Then I would say A1 equals some R1 times theta 1, where theta 1 is the distance, angle distance, or angle it makes with the real axis in the complex plane, right? So that's one way to define it. So I'm looking at a question by Amir. It says, when you expanded P, how come you showed that A1 absolute value squared and A2 squared with the length bars and not A1 squared since the other terms? Well, this is a calculational thing. We can talk about that at the end, I guess, right? We can try to maybe scribble here on the board and see how that works out. So there are a lot of questions, but I think I'll continue, and I think they might be answered as I go.
During your lecture, automatically the question will be answer will become.
I think so. Yes, I think so. I certainly hope so. Okay, so let's continue with this and see what happens. Okay, so this is where we were, right? We've got this experiment. We've got these expressions for probabilities and probability amplitudes. And so the question was, so why was I looking at that experiment? Well, because the experimental data that you do in a lab is what shows you that your state space is in fact complex Euclidean. You need complex numbers to talk about the probabilities and the physical behavior of these objects. But there's a little bit more that's going on, right? So as I said, we're not done with, let's just go through this somewhat quickly. First of all, let me bring forward how I'm going to talk about the Hilbert space that came up earlier. So what I'm saying is that the C2, right, the complex plane Cartesian product with itself is the state space of the photons that I'm talking about, right? So that is in fact a Hilbert space. It's a finite dimensional Hilbert space. Now, if you wanted to deal with infinite dimensional Hilbert spaces, where you're looking at your quantum object as having an infinite spectrum in the sense of, you know, infinitely many possible, you know, states, you need to get into a lot more measure theory and you know, more formal mathematical discussion. For quantum computing, it's the case that you can pretty much deal with everything in terms of finite dimensional Hilbert spaces. So we'll stick to that. So now I have 2 degrees of freedom in C2. I'll call them 1, 0, and 0, 1. I could have called them anything else as well, but these two work, right? You'll think of these states 1, 0, and 0, 1 as observable states, right? So you would say that these two states represent the situation where I was able to detect whether the photon went through the top or the bottom hole, right? So 1, 0 would be the situation where it went through the top hole in the wall, and 0, 1 would be the one where it went through the bottom one. Now, in general, if I'm thinking of my quantum states as being in C2, then I can make a general linear combination, or what physicists like to call a quantum superposition, right, of these two observable states. And I would get something called A1, A2, which is a linear combination of the two observable states. But again, note that complex numbers are R1, E, I theta 1, and A2 is something like that as well. And from here, I'll take out e to the I theta 1. And when I look at the length of A1 plus A2 squared again, I'll still see that I have the same expression for the probability as before, right? So this extra phase that I took out, so this extra term that I took out, which I'll call phase, right? Global phase, doesn't contribute anything in terms of when I try to see what the actual probabilities are. And so we say that anything that looks like A1, A2, right? And anything that looks like a simple R1 on the top and EI theta 1 taken out, they're all the same thing. They're equivalent to each other. So this is the global phase that gets ignored. It's a unit circle. And now if I shrink my vectors in C2, right? And again, C2 is 4-dimensional, so it's hard to visualize, but you can do this with some practice, I guess, by making some analogies with R3 perhaps. You shrink everything down to unit length, all your vectors, and then you identify opposite points to each other. You get something that is a sphere. And so now we're in a position to answer 2 questions that we had raised earlier. Why is the state space of quantum objects coordinatized by complex numbers? That answer has to do with what you see in the lab, right? With respect to the probability behavior of photons or electrons or any quantum object. To talk about this meaningfully, you have to have complex numbers. So we need complex numbers for that. Why did I call my state space of quantum objects before talking about the complex numbers as a complex projective space, which I call CPn-1? Well, CPn-1 can be shown to be the same thing as a sphere from which I've taken out circle action, right? So now this is getting very mathematical, and which is fine because we need this. But I did say I didn't want to talk. I was going to try to keep the mathematics to a minimum. So the point here is that you took away the phase, right? So when you take the phase away, you get yourself the space CPn-1. Now, if you take the special case of n equals 2, you get the block sphere, which is where you have your qubits. So now I'm going to start talking about qubits, right? This is the language of quantum computing that we use quite frequently. 1, 0, and 0, 1, which were the degrees of freedom in the vector space, are now sitting on, excuse me, opposite points on the sphere, right? And you label them as 0 and 1. These are observable states. And that's the block sphere. Sorry. Oops. So this is the the answers. These are the answers to the questions we had. Now notice that as soon as we have a sphere here, we are now looking at not the original vector space, but something a bit more twisted, right? And if I was to think of C2, the vectors 1, 0, and 0, 1 would be apart by 90 degrees, right? But here they're sitting at 180 degrees apart. So some kind of twisting has taken place in the process, distortion, when I took out the action by global phase. So what ends up happening is that you have two things that you're really talking about when you do quantum mechanics, right? And this is relevant to noise, of course. One thing is that you have a state space, which is a vector space. This is the, the Cn, C2, C4, right? The complex numbers, complex Hilbert space. And then you have this complex projective space that you kind of construct from it by ignoring the phase and identifying antipodal points, right? And how do these two relate to each other? Well, they relate to each other in the sense that we have this famous theorem from Wigner, which says that you can do all your dynamics, quantum dynamics, which would happen on the sphere, right? The block sphere and its generalization, which is the complex projective Hilbert space. Complex projective space. But all the dynamics would take place as unitary and linear functions on the vector space that you start off with. So there's an interplay of linear algebra. You still have your unitary operators, which you think of as quantum computations. We'll get into that just briefly. And we also have something more interesting on the other side, right? And I'll talk more about that interesting thing in just a second. So two things that come up again in this context are this movie that came out, AntMan and the Wasp. There were two good questions that came out of this movie. How do we enter the quantum realm from the Euclidean space where we live, and how do we come back to it, right? And apparently, both actions are fraught with danger, and that's what we want to deal with. The danger comes from the noise, right? That's kind of the claim. So why would this be relevant for quantum computing? Well, it's relevant because if I am a classical programmer, I would like to send data, load my classical data into the quantum space of quantum computations, right? So if everything is noisy in the process, that loading process would get corrupt, right? So I need to understand how this transition takes place. And why is it important to come back? Well, you're trying to read the data out, right? So that's why that's important. So an answer to question number one would be to say that, well, this is what we do right now, right? In physics, typically, is we say, okay, you tell me what the properties of interest are of your classical object, and you think of those properties as observable states of a quantum object, and then you apply unitary operations on those observable states and create a quantum superposition, and then you see what happens, right? This is what is also known as state preparation. So this is a noisy process as well. I mean, it's if it was not, we would have Grover's algorithm, which is a very well understood search algorithm and proven to give you an advantage in searching, right? We would have implemented this a long time ago on some kind of a quantum computer, but we still haven't in a very effective way. Of course, we have toy models everywhere, which is fine, but in a practical sense, we still haven't been able to do that. So that, to me, that question is still open. How do we enter the quantum realm? How do we send data into the quantum realm, into the quantum computer? How do we load the data? So while we're on the topic of applying unitary operations, a very interesting unitary operation you can apply on observable states is the one that creates entanglement, right? So perhaps we should talk about entanglement in just a second, but perhaps I can stop here and look at some questions again. Kunal?
Yeah, one question I'm getting, but no such question now. You can continue.
So on my chat, I have a Q&A, which has 11 questions. Let me just go through that really quick, Kunal, if that's okay with you.
These questions are already answered.
Okay, all right.
Oh, no. Sorry. There are so many questions, yes.
So I'm looking at the question which says, speaking of complex projective space, how come it is Cpn-1 where C does not have a superscript when describing a space of Cn? Or optionally, can you explain more about the projective spaces? More about what a projective space is. So if I understand, so if the question is about why there's an n-1 and not an n on Cp when I go from Cn, right? That has to do with the fact that you're kind of ignoring one degree of freedom. So you kind of say, I'm going to call it CP n-1, if that was the question from Amir. But I'll be happy to do this live later on, which might be a better thing to do. If quantum space is a sphere, would it be better parameterized using complex polar coordinates? So this is just an example of one quantum object, right? Like the states of one quantum object, one photon, one electron, with two possible states. So that's what this sphere is representing. If I have two photons or two electrons, it'll have four possible observable states, and its state space would be another much larger, complicated object. It would not be a sphere. Definitely would not be a sphere. It would be CP3, which is a complex projective Hilbert space of 4 dimensions, and you would still parameterize it using complex polar coordinates, right? But things would look a little bit more complicated than just what they look like on a sphere. Then I have a question here that says, as far as I know, many people are working on improving dephasing. What kind of techniques they're applying to improve the time? I honestly don't know, Rifat. Being a mathematician, I haven't actually worked in the lab that much, but it would be great if people talk to each other. I'm hoping to talk to some people in October who are actually working on this sort of stuff at an IEEE event and see what they're working on and how they're doing it. Another question is, why does the red portion of the expression doesn't play a role in classical? Because when you try to access it, right, the way you access it is using measurement, and measurement actually destroys that state, basically. You can't get it. It's a noisy process. And that's what the point is, like, how do we actually create a methodology, theoretical or practical, physically implementable, that will allow you to actually have that available to you so you can see what's going on. So,
Another question in the chat box. Do you ever think of a way of loading data for reverse operation? How could the data be loaded? What is your opinion?
How can data be loaded into a quantum computer?
Yeah, I think that's the question, but is the loading of data for reverse operation, how could the data can be loaded? Yes, right.
Oh, definitely. Well, first of all, the notion is kind of, it's an open question as far as I can tell. That is the point. What does it mean to load data into a quantum computer, right? Is your data coming to you in the form of an ensemble of electrons? If that is the case, then that's going to affect the quantum system, right? And it's going to create noise. So these are the issues that come up. So if you if there was a question about how people in the labs or the people who are working at IBM and Honeywell are doing it, I don't know. And I don't know if they'll answer that question because it might be proprietary information, right? So all I can do is kind of think on my own and see what are the mathematical ways to talk about this, and then sort of infer from that what they might be doing. And if they're not, then perhaps this can be a contribution to that end. So in fact, I think in the next slide, there might be some insights into that for the question that I just addressed. So Kunal, is it okay if I go back to the presentation?
Yeah, yes, you continue.
So, so let's talk about unitary operators and quantum computations, and then look at quantum entanglement in a little bit more detail. So really quickly, unitary operations are unitary matrices. These are exactly what you call quantum computations, right? A quantum computation is a unitary matrix, right? That's it. What is a unitary matrix? It's a matrix that has a property that when you conjugate, it has complex numbers in it, right? And if you conjugate those complex numbers, take the transpose, multiply by the original matrix in any order, you get the identity matrix. So in particular, it's a matrix that preserves distances. It's an isometry. Right? Here's an example of such a matrix. It just so happens I have all real numbers in here, but every real number is a complex number as well. So the definition still applies and still holds. This, in particular, this matrix that I had just put up is known as the Hadamard gate. what it does is that if I act with it on the observable state 1, 0, I get what's known as the equal superposition, right? Or uniform superposition of the two observable states. So yeah, what happened was that I was in one of the observable states, a classical state, right? And when I applied this gate, this quantum computation, right, on that observable state, I get something which is properly in the quantum realm, or more properly in the quantum realm than was just the state 1, 0, right? So this is the way you enter the quantum realm mathematically, right? But how does one implement this in the lab in a way that there's no noise in the system, right? How do I implement this? By saying, okay, I have classical data represented by the classical state 1, 0, and I want to send this into a superposition, right? So how do I do it so that I get exactly what I want? And it's a noisy process. It's not easy to do. Another more interesting example of trying to create or load data into the quantum computer, you could say, is a 2-qubit quantum computation. Here, what you do is you have a 4-dimensional complex projective Hilbert space. Things look like a superposition of 0, 0, 0, 1, 1, 0, 1, 1. A, B, C, and D are complex numbers. And when I apply these matrices, which are unitary, again, just so happens that the real values are enough, right? As I said, every real number is also a complex number. So when I apply these operations on the observable state 1, 0, 0, 0 of two things, two quantum objects, right? I get, again, an equal superposition of two observable states, 0, 0, and 1, 1. So this is what we call the entangled state, right? An entangled state. Now, mathematically, it may look kind of, whatever, right? So we did some calculations. So let's see if I can make a point of why this is so interesting and non-classical, right? So let's think of it this way. The idea is that entanglement is going to create stronger correlations than are possible classically between two objects, yeah? And I've got some, notation here, which may or may not be appealing to many people, but that's okay. Because what I want to do is actually get to this point right here, which says that my claim is that if I have a quantum state of two things, right? Two quantum objects, then by only looking at one of them, I can infer information about the whole system, right? And here's how I think about it in terms of classical coins first, right? So one might argue that, okay, well, that's no big deal. I can, implement that with just classical objects like coins, right? So let's say we take a look at this, right? We have two boxes and I have 4 coins. 2 of them are colored yellow, 2 of them are colored red. And what I'll do is I'll close my eyes, right? And shuffle these coins together and put 2 of them in one of the 2 boxes, right? Each. And then I'm going to take one of the box and send it to the nearest star system, Alpha Centauri. Okay? It's like 4 light years away. Somehow magically I do that. Well, magically, of course, right? Science fictionally I do that. And then if I take a look at my box on Earth, right? And I look at the coins inside it, and they turn out to be both yellow, I would immediately know that the 2 coins in Alpha Centauri box are both red. If I look at the coins on inside the box on planet Earth and I see them both to be red, then I know that the coins on Alpha Centauri are actually both yellow. And similarly, any other possible combination, right? Where it's kind of complementary, right? So if I see red, yellow on Earth, I see yellow, red on Alpha Centauri and so forth. So a lot of people think that, this is something, this is kind of a form of entanglement, right? And in some sense it is, right? You are inferring information, you're gathering information about the whole system by looking at only part of it, right? And this is what I had said in the previous slide about quantum entanglement. But there's something slightly different with this experiment and what quantum entanglement does. And what is the difference? It's the following. In this classical entanglement that I had on the previous slide, right? I had to look or measure the state of both coins in the box. to know what's what, right? I couldn't just say, okay, I'm going to put my hand in the box, right? Take out one of the coins, see if it's yellow, then I know something about the state of the whole system, right? The remaining 3 coins. I just couldn't do that. But in quantum entanglement, I can do that. And that's how it's different than classical entanglement. In quantum entanglement, I can look at just the state of one qubit and know information about the whole thing, the whole system, right? So one could say, okay, well, maybe we can mimic that classically as well by taking 2 coins and we weld them together rigidly with a strip and to give something like that, right? Here are 2 coins, a red and a yellow, and I connect them together with a strip. And if I toss them now, right, what will happen is that I'll see either 1 red and 1 yellow, right? Or the other combination half the time, right? So is this quantum entanglement? Is it mimicking it? It is. But now if you try to send one of the coins to Alpha Centauri, right, that would be quite impossible with this rigid strip connecting the 2 together. So these are some ways you can say quantum entanglement is different, and certainly quantum information and classical information are different, and certainly why we have to deal with noise when you go from classical realm to the quantum realm, vice versa. Okay, so I can take questions again. I'm getting into some stuff about measurement.
No such question. The question is that after your talk, can you talk about the brief your research? Okay.
Sure. Okay, so shall I continue?
Yeah, no, another question in the chat just come.
Okay.
I think moving towards, one question is, I think moving towards a parallel quantum computing may reduce the noise. The nature the time to be redefined. Okay, so he's saying that towards the parallel quantum computing may reduce the noise.
Okay, more of a comment than a question.
Yes, it's a comment actually.
Sure.
And another question is, said one of a pair of shoe, left or right. So related to entanglement, I think.
Yeah, yeah.
It's not a question. It's not a question, but it's related to entanglement, I think. There's a expression there actually doing. Okay. No other question, I think. No. Okay.
All right. So then, sorry. Go back here. So here's a little slide I had put together regarding quantum measurement. So what you see here is that you have 2 observable states, 0 and 1. These are elements of an orthogonal basis, right? With quotes in it, because this is in the projective space. Orthogonal doesn't mean 90-degree angles, it means 180 degrees angles, right? So what happens now is you say, okay, let's take a quantum state. Here it is. Here's a qubit, right? It's the state of a qubit in red star sitting on the sphere, right? And around that is a circle of all qubits that are going to measure the same. When I make a quantum measurement, they're going to give me the same result as this one. And how that happens is as follows, right? So if I measure this red state of the qubit, sorry, ignore that for just a second. I will get the result 1 with the probability which is equal to the length of this red line, and the result 0 with probability equal to the length of the red line. This was the yellow line, sorry, the red line here. And as I said, if I have another state on the same circle that I've drawn around this white star, right? That state's going to measure the same as this one. Now, if I had another qubit up here in a blue star, that will measure something else. It'll measure differently than the white star that I had before. It'll measure or be observed to be in the state 1 with probability that's equal to the length of this purple line, and observed to be state 0 with length equal to the length, with probability equal to the length of this green line. So that's all happening, you know, in the. I mean, you can imagine that I'm trying to understand how qubits behave while staying in the block sphere, right? The states of a qubit behave. Now, I'm producing probability distributions here, as I said, when I make measurement, right? Now, probability distributions live on simplices or simplex in the Euclidean space. And this is what they look like, right? So I've got the probability line. The line here represents the probabilities between 0 and 1. And they look like this line, right? Kind of part of this triangle. It's not the whole triangle, just the line. And I'm going to look at I'm going to take the state 0, observable state 0, and put it up here, and observable state 1 and put it down here. And from that point of view, then I can see that my probability distributions that were produced by measuring the states white star and blue star are those two dots on that simplex right there. Now, if I try to see, you know, how those lines, the lines in purple, yellow, green, and red appear in the simplex picture, that's how they appear, right? And this is how the other one appears. So you see that clearly distances are being distorted by measurement, right? I mean, there's a 180-degree difference between the observable states in the block sphere, but on the other side, it's only a 90-degree angle. But also, if I look at this distance right here between the two qubits, the blue star and the white star, that difference between those two is showing up over here, right? So claim is that this notion of quantum measurement actually distorts the picture, right? So you had some information encoded in the geometry of the block sphere, and when you make a measurement, you lose some of that information, and things get shortened or stretched when you move over to the Euclidean space. And in this slide, I have actually tried to do that a bit more formally. If I had the state A, when I measure it, so I'm looking at the third bullet point, this is a more important one. Notice that the second and the third bullet points are important. Notice that the probability amplitude was R2 e to the power I theta 2 minus theta 1. When you make a measurement, it simply becomes R2 squared. This is a unit complex number that goes to 1. It contributes nothing. The notion of measurement is so noisy that you lose all information about the difference of the two angles. And as we saw, this is where if not all, information about the quantum state was, right? So that's all gone. So this relative phase kind of decoheres when you make a measurement. So when you try to exit the quantum realm, that is clearly very noisy, right? This is a lot of noise in the system here. So again, how am I doing on time, Kunal? I'll try to keep it short then.
You continue, but try to make it short. Okay.
Okay, sure. So what was noise? The idea was that anything that changes the topology, the differentiability structure, and the geometry of your state space, right? That is what we consider to be noise. And as I had said, geometry would be fundamental, to the discussion here, and quantum measurement as well. So we're connecting the two here and saying that quantum measurement is a noisy process. It does not preserve geometry, right? What about differentiable structure and topology? I'll say something that'll take care of that automatically in just a second, right? So what are the million-dollar questions, right? The million-dollar questions right now for the state of quantum technology, quantum computing technology in particular, is how do we create qubits that are, fault-tolerant, fault-resistant in some way, right? Because ambient noise gets in the way, decoheres the qubit state, and we lose information. So how do we keep them coherent? And when I have somehow figured out how to keep them coherent in the Euclidean space where I live and from where I'm trying to program these things, I'm going to need to connect them in some kind of a hardware architecture. How's that architecture going to be built such that it's noise-free or noise-resistant, right? So we have these kinds of quasi-quantum hardware today, but they get pretty noisy after a certain number of qubits. So to this end, we need to introduce something called a manifold structure. And so the point is that, yes, there's a Hilbert space, there's a vector space in the background, but there's also a manifold structure, right? And this is what's going to be fundamental to know when we talk about Nash's embedding theorem and what kind of a toolkit it gives us. So what we have is a sphere, right? This is the block sphere where qubit states live. If I look close enough to it, it looks like the complex plane, right? So that's basically the idea of a complex manifold and also a real or Riemannian manifold, right? These are spaces which, when you look closely enough, they look like the Euclidean space. But if you were to somehow zoom away far enough, you'll see that there's all sorts of curvature, twists, and contortions taking place. The planet Earth is a nice example of a manifold, right? Locally, it looks like, it's completely flat, but when we zoom far out enough, we see it's curved. Complex manifolds will not be considered anymore after this slide. Our focus would be what's known as a Riemannian manifold. So let me just say here that the block sphere is a two-dimensional Riemannian manifold because it looks like the Cartesian plane, right? The 2 degrees of freedom when I look at things closely enough. And generally speaking, for 2 qubits, I have a 6-dimensional Riemannian manifold. For 3 qubits, a 14-dimensional manifold, and so forth. There's a nice formula that allows you to figure out what the dimensionality is. It's right here on the top. I'll let you look at it later on if you want. And now, to the point, what's an embedding? And then we'll talk about what a Nash embedding is. So an embedding is a function that is one-to-one, it's continuous, differentiable, has an inverse that is also continuous and differentiable. So this is this property of being one-to-one and continuous is called a homeomorphism. It preserves topological properties, right? So if we want to say, okay, there's going to be a topological distortion and it's going to cause noise, well, a homeomorphism, if that's your transformation, then there should be no noise in the system, right? With respect to topological distortions. Diffeomorphisms are functions that are the ones that I mentioned here that preserve differentiable structure, right? So for example, if I had this picture of differentiability in the sense that I have 2 points on the sphere where I'm approximating things with a flat plane, nice and smoothly, but if I change the shape, transform the sphere into a star with lots of points in it, then a lot of information about differentiability and rates of changes are lost at the points. I mean, things become ill-defined with respect to differentiable structure. So it's nice to have diffeomorphism when you talk about transformations of your state space to take care of noise coming out of that process. Embedding is not an isometry. It does not preserve geometric structure, right? And an example of an embedding is Whitney's embedding. It's basically, there's some statement here, which I'll leave here for you to consider. But basically it says that for 1 qubit, if I look at the state space of 1 qubit, I can make it look like R4 in a way that preserves topology and differentiability. If I have 2 qubits, I can make it look like the Euclidean space of that higher dimension, right, R12, in a way that preserves topological and differentiable properties. And for 3 qubits, I can make them sit inside R28, which is a very high dimensional Euclidean space, and things would be not noisy in that process. But still, Whitney's embedding does not preserve geometry. So we have to look at something that does, right? So let's look at Nash's embedding theorem, and that's the claim. This is the claim to fame, that it's an embedding, so it automatically does everything that Whitney's theorem did in the previous slide, but it does it isometrically. So not only does it preserve geometry, topology and differentiability, but also geometry. So if noise is coming from any of these three major sources, and I'm not sure if any other source I can think of that would be of noise, right, in a quantum system, then this embedding theorem would take care of all those noisy issues. Now, again, it's a mathematical theorem, some numbers here and dimensionalities. But the point is that if I have the state space of 1 qubit, I can make it sit inside a 10-dimensional Euclidean space in a way that leaves no noisy, fingerprint, if you will. Similarly, for 2 qubits, of course, I have to get into a very high dimension, R19, but there will be no noise in the process, right? And for 3 qubits, it's a very high dimensional space. Again, why is it worth it? Well, there's no noise in the system, right? It's just everything's preserved. And similarly for 4 qubits, right? It's a very high number, as you can see. So yes, there's a price to be paid with the dimensionality increasing, but accounts for all these errors that come up, right, fundamentally in the process. So what is the toolkit? Well, the toolkit is that, your fundamental question was, how do you enter the quantum realm coherently, right? Send a signal and start programming the processor, right? Or error-free or error-tolerant, fault-tolerant way. Well, this can be done by using the continuous and smooth preservation of fundamental mathematical features, right? Topology, differentiability, and geometry. And that can give you a whole set of programming tools which will be needed as you talk about in the near future, in the next generation of quantum technologies, about assembly language, right? What is firmware? What does that even mean for a quantum processor, a quantum computer? What is middleware, right? What is an operating system? You could certainly take the same model that's been around for decades, right, from classical computers, but you cannot take it as is. It has to be adjusted somehow to account for the quantum properties. And Nash embedding should be able to do that. Same thing with exiting the quantum realm. Do it without any noise. Measurement doesn't allow us to do that. Presumably, well, definitely Nash embedding should allow us to do that. Whether it's of any use, that's a different question, right? But in principle, it allows you to do that, right? And when it comes to reading the output from the quantum computer, that's exactly what you need. Okay, so this one, couple of more slides left, and I'll be done after that. Benchmarking, right? So Nash embedding can be used as a robust benchmark. So we have a first generation of, what a lot of people call quasi-quantum hardware out there, processors. What's the benchmark? What is the reasonable benchmark for their performance, right? Well, Nash embedding seems to be one of them, right? If not the only. I mean, I'm not aware of anything else, but certainly this allows you to figure out how to traverse the quantum classical divide in a way that's completely smooth with respect to most of the, physical properties that can lead to noise. This nice paper I saw on LinkedIn just the other day from IBM, it talks about a bottom-up approach they use to take care of noise in their quantum processor. And it's a great reading. You should all read it. I mean, I would recommend you read it. And it's a great idea. It's certainly a good idea. Makes logical sense that you try small steps, right? I'll try moving in this direction slowly. Oh, there's an error. Let's fix it, right? Sure, works fine. But at the same time, if there's a top-bottom approach available, right, which is what Nash embedding is, I think it's a great idea to try to combine these two approaches and see what you get. It can only help the situation. I am going to go through these fairly quickly, I suppose. So quantum computing is equivalent to reversible computing. So this is a claim.
One thing, you have a time, okay? You have a 30 minutes time, no problem.
Okay, all right. So I'll just slow down then a little bit again. Thanks, Kunal. So one of the claims that you can make immediately from Nash's embedding theorem is that every quantum computation can be replaced with the corresponding reversible classical computation, right? Now, this may have seemed obvious to many, and people see this, that this is the case. But as far as I can tell, to me, this became, factual, a theorem after looking at Nash's embedding theorem. Because what happens is that in the quantum state space up here, CPn-1 to CPn-1, you're basically saying I have a quantum computation that's going to transform my state of the qubits into some other state. That's a quantum computation, right? But because I have a Nash embedding, I can take those quantum computations and embed them down, send them down in a very faithful way into the Euclidean space where I can do reversible computing. So reversible computation is basically a classical computation which the output of which can be reversed, right? You can extract what the input was from the output. That's not the case in non-reversible computing. So Nash embedding would allow me to do that. And because Q is a isometry, it preserves length here. And reversible computations are orthogonal, they preserve length here. And because now I have a commuting diagram is what we call this in mathematics, everything's equivalent, right? So to build quantum computations or quantum computers, people should start focusing on how to build reversible computations is kind of the claim I'm making here. And what are the consequences, right? Well, the consequences are that we have a faithful representation of quantum computations in the Euclidean space, right? And this is the space we live in, and this is a space from where we want to manipulate quantum realm, right? The quantum realm. Well, here's a way to do it faithfully. Let me just quickly end with this example, sort of an example. The idea is that if I have a 2-qubit quantum computation like the one here, represented by a 4x4 unitary matrix, according to the equivalence between quantum computations and reversible classical computations, the corresponding classical computation should be something of size 19 by 19, right? Orthogonal matrix. So again, it's a question that comes up again and again. Well, you have something very small, and when you go into the Euclidean world where you're claiming things will be easy, it becomes really huge, right? Well, yes, that's the price we pay, but at least now I should have better control, right? I'm in my comfort zone, right? I'm a Euclidean entity. I live in the Euclidean space. This is where I'll do things, even if they look a little bit more tedious than what you would like it to be. But see, there's a way to do this, though, right? So once you have this reversible computation representing your 2-qubit computation, this one in particular, right? You can create an adjacency graph from this. Once you have the adjacency graph, you can embed that from R19. This graph will necessarily live in R19, 19-dimensional Euclidean space. You can embed that into R3. And embed means literally that. It's going to be a topology preserving process, right? So presumably, again, there should be no noise loss from loss of information or noisiness in that process, right? And there's a paper that I am citing here that tells you that you can always do that. And once you have a map inside R3, you can further send it down to R2 using a book graph, right? And these are methods that are well known from work done in classical computing. So this one in particular from Fan and Thompson, right? This one is in fact from, doesn't say the year, but it's an old paper. I like this one quite a bit. This was used for VLSI design, right? So the idea has been around for a long time. So point being that, when you have, you have a lot of stuff going on here, right? But of course you do, right? I mean, this is a difficult problem and you need to use interesting tools. And fortunately for us, all the hard work was done by mathematicians like John Nash, right? So all we have to do is figure out how to implement these things and go from there. One last slide here where I guess I should mention that there might be some connection between manifold learning, right? These are ideas from machine learning. And how you can take these ideas from data processing to quantum data processing using Nash embedding as well. And let me end with this final slide where I kind of just project as to what's going to happen, what the vision might be. The vision is that at some stage you walk into a natural preserve forest and you see steam coming out, right, from a hot spring, and it takes a very brilliant mind to realize that you can actually put that steam to good use and make a little toy out of it, right? And you know, a lack of warring maybe between between people, and even more clever people and incentives are needed to realize that, oh, that toy actually can be put to really good use, right? And you come up with the steam locomotive, which was the basis, you know, one of the fundamental factors that led to the industrial revolution of the 16th, 17th centuries, right? 17th, 18th centuries. Now, of course, we don't use steam locomotives that much. We use these maglevs, bullet trains, right? And we've gotten really good at supply chain and that sort of stuff using these transport mechanisms. So something like that should be probably happening in terms of quantum computing, right? So I think we're at the stage we have moved beyond steam and realizing that we can do cute things with steam, right? We've actually got a toy model, right? We have all these first generation quantum processors. And the question is, what kind of, you know, intermediate steps would be needed to go to something like, you know, a steam locomotive, and then of course eventually beyond. So that's what the story looks like to me, and I thank you for your attention. Thank you very much.
Let us take some questions from attendees. So
Okay.
this is not a one question that as earlier that your research area related to this.
Yeah, so my research area, so recently, of course, I've been working in, with respect to quantum computing, of course, I'm working in exactly this area, like how do you take Nash embedding and how do you, so I think I've figured out most of the details at the theoretical level, some of the details at the theoretical level, of course, there's a lot more going on in the background. But I think what I would like to see this research go is towards applications, right? And some of these things I mentioned in the talk, like can we use Nash embedding as a benchmark? The IBM Q, Honeywell's quantum processor, these sorts of things. Could we benchmark them against Nash embedding? Because I think Nash embedding is a more robust methodology. It's a systematic methodology that tells you how to actually go from one realm to the other and address the noise issue that comes up in very different ways, right? So that's the area I would like to take this research-wise.
And another question that could you give an example, or could you give a explanation, more detailed explanation, how the quantum computing will be carried out? For example, question is given that suppose we want to add two numbers in classical computer, then how we can do it in a quantum regime?
So probably the same way as you would do it in a classical computer, right? You would have to come up with a circuit, right, that implements the, and presumably in a binary setting. So if I want to add 25 and 62, two numbers, right? Presumably in a classical, in a calculator, right, classical device, I would represent them in binary and come up with some kind of an adder circuit, right? Full adder, half adder. It's been a while since I worked with these, but that's kind of the idea, right? You would want to have something similar, a quantum computation or a quantum circuit that implements that. Now, of course, here things are going to be a little bit different, because if you don't deal with measurement, noise coming from measurement or noise coming from other sources, then ultimately you have to sort of get an answer that is probabilistic, right? And that happens today as well, right? If you look at D-Wave's annealer, for example, quantum annealer, specialized quantum computer, it says so, like you have to run the problem several times and look at several different answers, and then you get this, you're kind of sampling the answers, right? And trying to see which one's the best. So this doesn't happen in classical computing, because you've got a very well-controlled notion of noise, right? And ways to deal with it. Noise at the quantum level is more dramatic. So we have to deal with it. So I hope that answers the question, that you'll need some kind of, quantum circuit that does it. And I think that if you do a Google search, you should be able to find some. I know that Marek Prakowski, who was my allied area advisor at Portland State, has worked on these things in the past. and with some people in Bangladesh, in fact, who were working on this in those days. So, yeah.
That is some error circuit will be worked. Adding two numbers, just some simple error circuit will work in a quantum computing.
Yes.
Any other question? Let me check. Yes. One is the question that is a Nash embedding is coherence?
Yeah, so I see that, right. I would like to say so, yes. I would say that in theory, right? In theory, it's telling me how to take a qubit state and make it inside the Euclidean space, right? And the question, so this is at the state level, right? So really the question, so this is Itamar, right? Yeah, that's the question. So now the question is, okay, I've got the qubit state sitting inside the Euclidean space, right? Is there some kind of a measurement that I still have to make on the Euclidean image? Or is it somehow a bit more of a deterministic process now, right? I don't know the answer to that. I mean, my feeling is that it may be the case that I mentioned Whitney's embedding theorem earlier, right? Which is very closely related to Nash embedding. The only difference is that Whitney's embedding is not an isometry. So my impression is that quantum measurement is perhaps a Whitney embedding because it preserves topology and differentiability structure. Right? Certainly, I'm more inclined to believe it preserves topology at the moment. But if that's the case, then there might be some way to develop algorithms that extend the notion of quantum measurement, right, into a Nash embedding process. And perhaps then we could say that Nash embedding is coherent or is actually defining coherence. There's quite a few questions that are, of course, completely open.
Okay. Another one question that is related to the Nash embedding approach to space engine in support of modeling proposed ion path as a compared with thrust ratio in an advanced population system.
I didn't understand the question, Kunal. I'm sorry. Could you repeat that?
Following related to Dr. Khan, would you be interested in following a Nash embedding approach to a space engine in support of modeling a proposed ion path as compared with thrust ration in advanced propulsion system?
The question has to do with ion propulsion?
Yeah, ion propulsion, ion path, maybe ion propulsion system.
Okay, good. Do you have the question? Maybe I can read it directly.
That I copying in a question answer pattern.
So where would I see it?
The question's posted in Q&A, the last question.
Okay. So it says, would you be interested in following a Nash embedding approach to a space engine in support of modeling a proposed ion path as compared with the thrust ratio? Is it supposed to be thrust ratio maybe in an advanced propulsion system? So that tells you that I don't know much about propulsion systems.
Yes, this is our propulsion system.
Yeah. So I'm trying to see how I can approach this because if the spirit of the question is about connections between special relativity, general relativity, and quantum mechanics, then certainly there are, so just like, in quantum mechanics, we're talking about how to embed the quantum space into the Euclidean space. There's an equivalent or similar idea where you try to embed the Lorentzian space into Minkowski space, right? And which basically says you can take models of general relativity and kind of make them sit inside a basic fundamental model of special relativity, the Minkowski space, right? So is there a connection between these two? I would like to see one. And I think this is kind of going towards the fundamental problem of like, why can we not reconcile physics and relativity, right? It may be that you have embeddings from in one realm and the other, but not across like that. Or maybe we're just missing something. The idea would be a bit more applicable to relativistic quantum information processing, which is of interest right now for people who are working in open air quantum communication between Earth and satellites. So I think a lot of Chinese groups are really active in that. So this would be highly relevant there, but I'm not sure if people have looked at this. I know there was a lot of people, groups in Imperial College, I think, well, in the UK in general, who were working on relativistic quantum information, and I have not seen anything similar to this addressed in those groups. But I'm unfortunately not in a position to say much about propulsion from an engineering perspective, or because I just don't know anything about it. Thank you all. Take care.
Thank you, Dr. Faisal. So you'll provide us the slides, right?
Yeah, I can send them to you, Dave.
Okay, thank you very much, Dr. Kunal Das.